Welcome, everybody. Today we're gonna start looking at the first examples of multi-agent algorithms to solve games or stochastic games. We had previously just looked at um, non-repeated general sum games where there's only a single game state for the agents to interact in. And now we're going to look at some situations where the games can have multiple states. Well, we had previously covered this in earlier chapters, but the games, yeah. So here's a little something. So for normal form games, we get looked at in chapter 4. There was just this single sort of payout or reward matrix that would define how agents would receive reward depending on the joint action. What's shown here is just the simplest game you can have, which is just a two action, two agent game. And there's been a lot of study on these and their properties and the different sort of equilibrium solutions. But, for these games, the policy would just, you know, be tell an agent, or in this case, if it's a joint policy function, it would just tell either the combination of agents or each agent individually which action they should pick, and then the combination of the two actions would determine how the game outcome would appear in one of these four squares. Then in stochastic games, we just extend this to have multiple states, but now, unlike in vanilla like MDPs we looked at in ordinary reinforcement learning, each one of the states is now a normal form game. And then after the actions are selected, there's some probability of transitioning into potentially a different game state. I mean, this is drawn as in a very abstract way, but one of the first examples we'll use in this chapter, really, we don't like what's more important about that example are the different states, and there's like a lot of them here. We're just showing three, and each state is not, we're not really going to bother drawing it as this kind of 2x2 game grid or however many joint or actions there are per agent. So we had really delved more deeply into like these 2x2 games in the previous chapter, but for looking at stochastic games, we're going to look at more of a grid world setting where it's going to be hard to actually visualize the game like this, and we're also going to not really consider competitive situations yet. That's going to come in later chapters. We're going to only look at sort of cooperative settings in games where the reward is shared, or there's some reward goal that's shared among all the agents. Whereas a lot of the interesting cases in these 2x2 games are competitive scenarios where the agents are competing against each other, which is very interesting in terms of game theory, but also introduces a lot of problems in multi-agent learning. And then, yeah, like the most complicated example, which we're not going to get to yet, but it's introduced here to have an idea of what information the agents will have to draw upon for their policy decisions, are these partially observable stochastic games. And the purpose of these is for situations where the agents may not actually have access to all the information in the state. Like if all the state information includes everything relevant about the agents and the other agents and the actions the other agents take. So if we have a problem we're solving, which is just a normal stochastic game, then each agent will have access to this entire history of the states and actions from the other agents. And this history is not used when we do reinforcement learning usually, because the Markov property of the environments means that we don't care about the state action history. However, in reinforcement learning, we're just dealing with a single policy, and the dynamics of the environment only depend on the environment transition function, which has the Markov property. When we have a multi-agent problem like this, what happens in the game and also the importance of what happened in the past depends on the behavior of the other agents. And the other agents could be changing over time. their behavior could be completely unknown. They certainly don't have this Markov property. So in order to have any success at forming a policy function, we need to actually look at that action history so we can understand, you know, like how the dynamics depended on the actions of other agents. Later on, when we look at these partially observable games, now we're not going to give the agents access to the whole state action history. Instead, what they're given is a history of observations. And these observations could just reproduce this whole history, or they could be some subset of it, like in the case where the agents have a limited horizon they can see. Maybe they can only see agents that are close to them, or they can't remember infinitely far into the past. And those are all, limitations that we'll deal with in the partially observable case. But to start out, we're going to take this case, and actually this whole history thing we're not really going to deal with until chapter 6, because the algorithms in this chapter are going to reduce the problem in some way so that we can basically apply a technique which looks almost identical to what we would do in ordinary reinforcement learning. And that's really the crux. The important part of this chapter is introducing how we can do that reduction, and then also what are all the problems and limitations of applying that reduction. There's also this discussion, which, again, like this chapter doesn't actually analyze any of the algorithms with this criteria, but this is more preparing for what's going to come later in the book, where we're looking at, in theory, one of these games could have some optimal policy or optimal joint policy. And that is going to depend on sort of what kind of optimal policy we're looking at. It could be an equilibrium solution, like one of the Nash equilibrium solutions, or, and then we have to decide which one of those we select. But normally, when we say that an algorithm converges, it's that whatever joint policy the algorithm learns, which is like the joint behavior across all the agents, is just going to equal this, theoretical optimum policy. And then there's all these weaker convergence criteria. Oh, actually, these slides don't even go into it, but or maybe I'll actually go back to what the book says about this. But there are these weaker convergence criteria, such as having the return converge. So like, even if the policy doesn't match exactly, if we learn a policy such that the expected return for each agent under the policy is equal to the one under the ideal policy, that would also be considered a form of convergence. And then there's also, more average forms of convergence, where here it's like that the average return converges. But these are all weaker criteria. And normally this criteria, will imply all of these others as well. But this is more of interest to just theoretically analyzing algorithms under really strict restrictions. Whereas, a lot of the time we're not even going to necessarily know what this optimal solution is for some of the problems that we look at. There's another way to look at the convergence. It's mentioned here where, it may not be computationally practical to check for these properties. So instead, what happens is often we just look at the return that the agents get, which is just like looking at the learning curve, and to see when the learning curve converges to something, if it does converge. It's possible that the learning curves for the different agents could actually fluctuate up and down with some games. But if this does converge, then at least we know that something has stabilized. However, just because the expected returns converge to some value, it doesn't actually mean that we've reached one of the solutions that we care about. But it is a way of at least knowing that there's no point in running the algorithm any longer, because the performance across the agents has stabilized. to some value. So these are, this stuff will all come up later, but for now, we can focus on how we're going to take the first steps into multi-agent algorithms, which is single agent reductions. And the good thing about these reductions is that if we already have a bunch of tools from reinforcement learning, we can apply, any or all of those tools to a multi-agent problem once we have transformed it appropriately. So there's two approaches that are discussed in this chapter. The first is central learning, and this is that we imagine that there's some central agent which is directing the behavior of all of the other agents. So then it just looks like a normal reinforcement learning problem, except there is one problem. So we can take the joint action space, which would be all the different combinations of joint actions the agents could take, and just consider that as our new action space. And then we already have the state space. But when we look at ordinary reinforcement learning, we need to have this reward signal for every step. But in a multi-agent problem, each agent is going to get its own independent reward. So the problem, in order to do this, we are going to have to apply a transformation to the reward we get to turn it into a single value. And for some problems, that will be easy. And for others, it will be completely impossible, and this approach won't work at all. The other idea is to have each agent perform their own RL algorithm, where they're trying to learn their own personal optimal behavior in the environment. And we have the algorithm basically manage the actions of all the other agents, but each agent only sees the transition that occurred from its own action. So from the perspective of each agent, it's just taking the environment and the behavior of all the other agents together as like its environment. And then each agent can learn its own, try to optimize its behavior in that environment. So this works. We don't have to actually do anything with the reward signal because each agent is already going to get its own reward signal. However, this presents other problems, like now the agents are not actually in the type of environment that we would expect for reinforcement learning because it's not a stationary environment anymore. It doesn't have the Markov property. It's changing over time because the other agent's behavior is affecting the environment. And also, this applying independent learning to a problem may not actually converge to what we want. In fact, it may not converge to anything. So that's another problem. And this depends on the properties of the actual stochastic game that we're looking at. But the easiest thing to look at first is central learning. And I mentioned this, that we do need to transform the joint reward into a single scalar reward, because in MDP, right, when you have a transition, you produce a new state and a reward. So we can't, deal with multiple rewards. We have to combine them in some way. Now, if we have a common reward game, it's trivial, right? Because then every agent, by definition, always gets the same reward. So we can just use the common reward. But, a lot of times, like we looked at zero-sum games previously, and in zero-sum games, then the agents are competing with each other, and we could sum the rewards, but if we sum them, the sum is always zero. So it's a worthless signal. And in a general sum game, we could also have competitive scenarios, and the actual difference between the rewards matters. And actually, for the equilibrium solutions that we looked at last time, there is no scalar transformation that we can apply to the joint rewards to learn anything that would be like an equilibrium solution. But in cooperative games, like whether it's, even if the agents are getting separate rewards, but if our goal is actually to maximize the sum of the rewards, then we can just apply the sum and then learn according to that. And we should learn something that does maximize the reward sum. But that type of goal is only relevant in, cooperative scenarios, which is useful for some games. Like there was, I think, an example mentioned earlier in the book of like a bunch of warehouse robots that are trying to do something in a warehouse. And in that case, we just care about their overall production as a whole. And we could use this scalar reward approach where we just sum it up. But this will not work in any kind of competitive setting. The other challenge with this is that we need to have the joint action space like enumerated for this. And the joint action space will be enumerate all the different combinations of actions across all the agents. And this space will grow exponentially with the number of agents. And if there's too many agents, it could become computationally intractable. And yeah, I mean, this is another point which isn't always relevant, but obviously you can't do central learning if the agents have to operate independently, because this depends on something seeing all the agents and disseminating the information about what action they should take. So if the agents actually are independent entities that aren't going to be connected to something, centrally, then this approach also will not work. So there's this pseudocode here for central Q learning. But actually, if we do this reduction here, a better way to think about it is that the work we have to put in here is transforming the problem into an MDP. Once we do that, we can actually apply any reinforcement learning technique to the problem, right? It doesn't have to be Q learning. It could be anything, right? And we have like, if you want to go back, so here, like this notebook, sorry, this is from the like Sutton and Barto material, but this we had reviewed a while ago is just a summary of all the different tabular solution methods for MDPs. We can see in the table of contents here, we have these exact solution methods like value iteration. We have sampling methods, which includes Monte Carlo methods, and also Q learning is one of the temporal difference methods. And there's also all these variants of Q learning and like expected SARSA and double Q learning. But really, if we apply the central learning, we now are just back in the realm of ordinary reinforcement learning, which is not the focus of this book. But what we do have to look at carefully is to understand how we do this reduction for central learning. And then once we do the reduction, we can apply any of this stuff. So I haven't actually written that much code for this yet. Like most of what I've written, I showed some code last week, which involved these two-player games. And this was more stuff just to demonstrate the different types of equilibrium solutions for games with these 2x2 games. But this is just sort of for visualization purposes. Here, this chapter gives enough material to start thinking about how to organize, how we would structure code for actually writing multi-agent algorithms. And the first thing we have to think about with this is how do we have the transition functions? Like the environment is really determined by the transition function. Everything else is just extra information we need on top of that, like the state space, the action space. Those things are necessary, but what really makes the environment work is the transition function, which is what determines what state and what reward results from a joint action selection. So if we look back, this is all kind of based on how I had defined these types for ordinary reinforcement learning. But in ordinary reinforcement learning, like we have this here, I'll look at a more simple example. Let's just think about like a deterministic problem where we have, a state action pair, and then for the state transition, that will map to a new state, in which case this in that case would be a matrix. Yeah, the reason why this has multiple dimensions is because it's also suitable for Markov reward processes, which don't have actions. But for a Markov decision process, we have this matrix which will store the transition state for that state action pair. So this is like for a tabular deterministic problem where we can write down all of the transitions, all the states, all the actions, and we can just create like lookup tables for all the different dynamics in the environment. So in this case, because it's a single agent problem, we have like the state action pair, which is just two inputs we have to worry about to look up the transition. Now, in the multi-agent problem, I've created this transition type. We saw these maps. So this map will provide the transition state, and this other map will provide the reward. And the way I've organized this is if we have a multi-agent transition, it has this T as like the type of the reward. So it'll be some numerical value. The N here, this is the number of agents that exist in the problem. NP1 is just, need this for convenience, but this is just, there's an added dimension here because for each agent, there's going to be an action for each agent. So there's going to be n actions. But in total, if we have these transition maps, we also need to include the dimension for the state that the problem is in, because there's more than one state. So we need to add 1 to this value of n, and this is just another type parameter here. And then for a deterministic problem, which so far in this, I've only implemented this for deterministic problems. For a deterministic problem, all of the members of this array will just be integers. And the integers will correspond to the state that you end up in after that transition. And then for the rewards, in a deterministic problem, this will just be a list of n reward values in this array, which will have, this, again, n+1 dimensions. But these reward values will then, there will be one reward per agent, right? Because in these problems, we always have to provide a unique reward for all the agents. This is for a general sum stochastic game. If we have a zero-sum game or a shared reward game, then we're actually back to the scenario where, well, here we wouldn't actually need this tuple of values. We could just get away with having a single value for the reward because there's some restriction on the game. But in a general sum game, each agent can have an independent reward. So yeah, I have a concrete example of this, which will make it a little more clear. But this is the characteristic of all these tabular problems, which is that we can just represent the entire transition function as a matrix, or in this case, a multi-dimensional array.
So Jason, can I ask a quick question?
Sure.
So in life, a lot of times there are dependencies between the optimal state and the state of multiple variables or agent outputs. In other words, if an agent is making something better, taking a step and from his perspective is better, the overall might get worse, or somebody else's target might get worse, right? You're not covering that case, right? You're talking, when you say general sum, it means that everybody is contributing in the same direction if one optimizes its state. Is that correct?
So for central learning, what is optimal depends on the scalar reward function. So if we sum the rewards for all the agents, then this will actually find the optimal solution that coordinates all the agents to maximize the sum of the reward, or the product of the rewards, or any scalar function you could apply to the rewards. It will just find the joint policy that maximizes that. In cases where, about when I was talking about general sum games here, general sum game just refers to a game where there's no restriction on the rewards allotted to each agent uh, from a decision. Like if we look at this, like this is like a 2x2 game. This is a general sum game because if you look at each possible outcome, and this is like the rewards for each agent respectively, there's no relationship between these rewards. Like here, like the reward sum is 8. Here, the reward sum is 3. Whereas
Right.
like in a zero sum game, if we looked at the sum of the two rewards, it would always be 0. Um,
Right.
and where so general sum game just means that we really do need to share the individual reward for each agent.
Okay.
In
Okay.
all other cases, like in a zero sum case or a constant sum case, well, actually, no, constant sum is different, but in a zero sum case, which by the way only is relevant for two agents anyway, then the rewards are always the negative of each other.
Okay.
But in terms of the agents coordinating or not, this single agent RL reduction creates a new objective for the problem. And that objective is based on the function that takes these n reward values and turns them into a single value. So that could be just the sum function.
Right. Right.
And in that case, we would be optimizing the total reward accumulated by every agent. And yeah,
Okay.
one agent would, I mean, each agent isn't actually making its own decision. There's just a central party telling all the agents what to do. And that
Right.
central party is only interested in maximizing this scalar function.
Okay. Okay. Got it.
Yeah.
You,
However,
you spoke you spoke earlier about the optimization taking place within an agent under that case.
independent, yeah, we'll get
Yeah.
to that in a second. That's an
All right.
independent learning.
Yeah, yeah, yeah. I guess that now that I say it out loud, that was really my question is the independent learning and
Yeah.
then the impact on other agents learning based on its
Yeah,
optimal.
we'll get to that
Okay,
later. For now,
okay,
we're just
okay.
looking. Yeah. So, but this whole thing, this is just to set up the framework of any multi-agent problem. Um, and then this is one of the pieces we need to convert this into to do a single agent reduction. So what this function does is this is actually taking this notebook imports this code from the single agent RL. So this why like this tabular RL, this is like this package you can get actually in this. It's all in this GitHub repository, which should be in the meetup link. You can find it. But all these older code bases I'm referring to are in this repository based on the Sutton and Barto stuff. So what this is saying is this takes a transition function, a multi-agent transition, and a reward function. This is the scalar reward function here that would, just take the tuple of rewards and turn them into a single value. And then it produces a new transition function, which is a tabular transition from ordinary reinforcement learning. And in order to do that, there's what these steps are doing is it's measuring the dimensionality of the state transition map. But all of this, it's a little abstract and hard to visualize. So normally, like this would represent a transition map. So I already mentioned for the reward transition map. Oh yeah, actually no. In the array, there's these tuples stored. So if we have two agents with 6 actions each, then actually just imagine that each of these numbers here is like the tuple of rewards for the agents. The important part about this is actually seeing what the array looks like. So now, because there's 2 agents, and here I'm just picking that there's like 100 states. Now, this transition map now represents the reward value that an agent could get for all the different possible joint actions. And the way I'm indexing it is the first two indices represent the action from the first and second agent. And then the third index is the state index. So if we go through this, like each one of the states now has this 6x6 grid, which says, for each joint action, like it. So this, if we take this slice, this is like if we're in the third state, and then we have, the joint action 1-1. This is the reward that the first agent would get, or there could be two of these values to give the reward for each agent. So we have this map like organized like this. Now, and you see that there's like a new one of these 6x6 slices for every, right? This is a 6x6 by 100 array. Now to turn this into a MDP problem, we need to take this whole thing and turn it into a matrix. But I'm just going to use the convention that I always index things with the same style. So because I'm putting all the action indices first, if I reshape this whole thing, like here, if I reshape this to have length, or like, rows equal to 6 times 6, which is the size of the joint action space, and then the same number of states, now I've just remade this into a transition map for an MDP, where now the rows represent all the different possible joint actions, and the columns still represent the states. But the important thing is that the final dimension of this is the state dimension, and then the initial dimensions are the actions, and each agent will create a new dimension in this array. And this makes it really easy to just reshape this into the joint action space here. But I'll show another example of how the indices work. But the basic idea is we need to take this thing, which is this array of dimension n+1, and then each element in the array is a tuple for each of the agents. We need to use the reward function to turn this tuple into a single value. And then we need to reshape it into just a matrix. So this n+1 needs to just go to 2, because now the +1 is the second dimension for the state space. And then the first n dimensions are going to be unrolled into just a single dimension, which is the size of the joint action space. That probably is a little confusing, but I'll show a more concrete example of how this unrolling works. But does anyone have any question about this already before I get into the more specific example?
Well, so far I don't really have a question here regarding the joint state representation where basically the state space is the number of agents and the entire state space for each agent on a tabular example.
Yeah, well, actually, so the state space will be the same for the multi-agent and single agent problem, because like the state will include the position of all the agents, everything else relevant. The transformation we really have to apply is to the action space, where instead of having, in this case, like there's two agents with 6 actions each, so we can index this with a 6x6 by 100, or the number of states array. But the joint action space will have size 36, which is 6 times 6, which represents, right, all of the different combinations of joint actions that can be taken. So this is handling the transition functions in the tabular case. Now, to make an actually, I need to rename these types, because I was just using the same naming convention, but these actually would not be called MDPs. Like these would just be called multi-agent stochastic games, at least in the terminology of this book. So what does one of these games look like? Well, we could compare it to, I did this for a tabular MDP. So when we have just a normal, right, Markov decision process, we have the state space, the action space, the transition function, which could be a lot of things in a tabular, like deterministic problem. This would just be, two different matrix maps that would tell you exactly what happens for each transition. Then we have this function, which is important because it initializes the state index. In these tabular problems, this is what we did for single agent reinforcement learning. Because we have a complete list of states and actions, whenever we refer to a state or action, we'll just use the index rather than the actual thing. And we can always convert that to the state later. But for simplicity of actually writing code, we always know that we can get everything we need from the index. So we need a way to initialize the index. It could just be a random selection, but usually with problems, there is some sort of initial state which is distinct from a random state. And then this bit vector will just also provide a lookup of which states, if any, are terminal states. Terminal states are just ones where there are no transitions out of that state. So if we're keeping track of an episode in an environment, it would just mark the end of an episode if we reach a terminal state. And then these things are just convenience functions that allow us to remap, look up the index for a state or an action. So now if we compare this to the multi-agent case, we have still the state list. Now the action space is going to look different. Now we have agent actions, and instead of now having a vector of A, we have an tuple of length n, where n is the number of agents. And this is so that we can have potentially a different set of actions for every agent. Sometimes it'll be the same for every agent, but in general, we could assign different possible actions to different agents. And then we have the transition function, which will be one of those things I showed above. We have the state initialization, terminal states. This is also the same as before. And then these are the lookups for mapping states and actions back. These things are just convenience functions so that some of this stuff will be automatically generated if we try to create one of these problems. Like it'll automatically generate the state and action index. So really the main difference between a multi-agent problem and an MDP is that this now is a list of actions. N lists of actions as opposed to just one. And then the transition function is going to be one of these multi-agent transition functions rather than the normal transition function, where now, right, we're going to have one of these multi-dimensional arrays involved in looking up what the transition looks like. Yeah, so in order to take one of these multi-agent problems, and this is what we need to do for one of these central learning methods, is that we have to take a multi-agent problem here, which is not an MDP, so this will be a stochastic game, and we need to convert it into an MDP, and we need to provide this reward function. So if you look at this, all of the things here that are like this, like MDP.states, MDP. All these things are just passed through unmodified. The things that are modified is the joint action list and the transition function. So I already showed earlier how this thing up here, which converts the transition function by reshaping these things. It reshapes the things, and also you can see here the reward transition map. Here I'm applying the reward function to each of the rewards right here. This thing where I reshaped this here, but still each element in the reshaped array is a tuple. So this reward function takes that and converts it to a scalar value, which we need. So this will turn it into a tabular transition. But then the other thing we need is to create the joint action list. And this will be a list of all the joint action, all the joint actions here. Now, I am just using this Cartesian indexing convention, which is the convention used when you reshape a multidimensional array and flatten it out. And this way, you don't really have to think about how any of the indexing works as long as you're consistent with how you do the indexing. So the convention I'm using is that the first set of indices are always the action indices for each individual agent, and then the final one is the state index. So as an example here, what this is doing inside of here is that this is an example test where, like, let's say that these are, this is the agent action space. So each agent has 6 actions, and there's 3 agents. So in the multi-agent stochastic game, this is what the action space would look like. Now, in order to convert this into a single agent reduction, we need to look at what these indices look like when we produce joint actions. So when we index this action space, we would index it like 1, 1, 1 would mean agent 1 is action 1, agent 2 is action 1, agent 3 is action 1 in its own action list. And this little reshaping of the Cartesian indices, forming this multidimensional array, this is what the joint action list looks like. Imagine that, let's say instead of 1 to 6, there was actually like something named in here, like the actions had an actual name to them. It wasn't just a number. I mean, it would still be indexed 1 to 6, but in order to form this joint action list, we just look at the appropriate index from each one of these, right? So this is like saying, select the second action from list 1 here, and the first action from list 2, and the first action from list 3, and then form this new joint action list where now this is of size 6 to the 3, right? Because this is going to contain all the different combinations we could form from 1 to 6. And you can see, right, there's just some numbering convention here. And now I'm going to use this index, 1 to 216, as the new index for the joint action list. But I can always go back to see, like, okay, what does it mean to pick joint action 216? Well, it just means that I picked each one of these actions for each of the agents in the joint action list. So does this make sense to everyone? Like how the joint action space is always going to be this, each of these lengths multiplied together. But, once we take care of all this annoying indexing stuff, right, then we're free to just apply any out-of-the-box RL algorithm we already have. So actually for this, okay, I guess the book handles this a little bit differently, but to make this a little more concrete, I'm just going to skip ahead to this example to actually see what we're talking about with. So this example will serve as sort of the grid world test case for multi-agent learning. When we did tabular learning, we often use this grid world type setup to study algorithms. And maybe I can show, like, in the grid world environment, we just have some initial state. There's a goal state where you get reward for reaching the goal. And then there might be obstacles or other things that perturb the agent. But here, the agent's goal is to just reach the goal and get the reward and reach the goal as quickly as possible. So this is a common test case example for reinforcement learning. So the analogy to this in multi-agent learning is this level-based foraging example. And this is a grid world, but in order to make the grid world interesting for multi-agent learning, we have some number of agents. Here there's 2. And then there's some number of items. These items replace the concept of a goal state in the grid world example. And now instead of just reaching the goal of the agents is to collect these items. And the items have a level associated with them. The agents have a level. And the idea is that the agents can move in the grid world, and then they can collect items if they are adjacent to an item. And they can only collect an item if their sum is greater than or equal to the item level. Or sorry, their level sum. So in order to collect this apple, this item in this example, because both agents are level 1, they would have to both be adjacent to this item and both select the collect action. And then they would collect it. If only one of the agents tries to collect it and the other doesn't, its level would not be high enough to collect and it wouldn't work. So with this type of problem, you can create scenarios where the agents have to cooperate if they want reward, or some of the items can be collected by a single agent. So does this, any questions about this example, how it works? I didn't actually say how the rewards work, but basically an agent will get a reward for collecting the item. And here you get a reward of 1/3 for collecting this apple. And then both agents would receive 1/3 for collecting this. So their sum reward would be 2/3. But the total available reward in this, if we sum across all the agents, is 1. Because it would be 1/3 for this, and then another 1/3 for each of them for this. So with central learning, we could take this problem. We could say we really care about the reward sum across the agents. And if we apply a discount factor like this, then we care about the reward sum across all the agents accumulating as fast as possible, which basically means that they collect the items as quickly as possible, accounting for, the level of the items and how fast you can collect items with different levels. Because here, like, there's different rewards you could get at different times. Like, this apple can be collected sooner than this one. So with the discount rate, it would get, a higher reward. Like, it wouldn't be as many steps in the future to collect this one. But, the goal here is just to collect everything as quickly as possible. And if we do it where we care about the reward sum, then there's no competition between the agents. If we do it this way. Does this example make sense?
So do the agents have a shared perception of the environment, or does...
Oh, sorry, no, back here. You're a little quiet if you're trying to ask a question. If you could just, can you turn your volume up or speak a little louder? It's still really quiet to me anyway. I don't know if anyone else can hear better.
I couldn't hear him either.
Okay. Yeah, you sound very quiet. You could also type your question in the chat, or see, but you can try again. I don't know.
Can you hear me now?
It's still pretty quiet. I can maybe hear you if you, but here. Well, why don't you ask your question? I'll see if it's loud enough for me to hear.
Oh, can you hear me now?
Yeah, that sounds pretty good.
Okay, yeah, I just needed to change my mic. But yeah, I wanted to ask, so do the agents have a shared perception of the environment, kind of like a hive mind, or do they each have their individual slices of the environment that they perceive?
So for this problem, because it's a stochastic game and it's not partially observable, the agents would be able to see the entire environment. So where the other agent is, where the items are, and also they can see the actions of the other agents, but actually for the central learning algorithm, notice that there's no like history here. So when we do single agent RL, there is no history, and that's because
in the more complex like implementations, could you have like an agent having only a certain like field of view? And then
that would
some
be
agents based off the communication could have some shared portion of the field of view.
Yeah, that would be for like a partially observable problem, and then
Oh,
that all is will be discussed in more advanced algorithms. But this is just the very first steps in how to all these methods of reducing the problem to a single agent problem avoid all of that complexity.
yeah, I see.
But
Yeah,
there
because
are
one of the things I was thinking, so if the agents if you can adjust the level of communication between the agents, then they would be able to have access to certain amounts of other agents like fields of view, and then you can essentially model that with like a graph network and like the message passing scheme.
well, I think communication between agents is also something you can look at. Then the action space for an agent becomes larger because an agent can choose to either make actions, in this case like a move in the environment, or send a message, and then you have to define what the space of possible messages are. But it becomes quite complicated if you allow communication. I don't know if the
Oh yeah,
book actually goes into any algorithms that really do use communication. I know in practice, a lot of the even really cutting edge stuff people have done with multi-agent problems, they often have no communication between the agents, and they just attempt to learn where the agents can just observe, and any kind of communication between the agents would have to occur through like indirectly through like signaling, through how they behave.
yeah. That seems like it kind of
Or
creates a
yeah.
combinatorial explosion.
I mean
Although it's
there's ways of handling it. It just it's complicated. So but we're certainly not going to get to that here because we're not even actually looking at situations where there's a partially observable environment.
yeah,
Like for this case,
cool.
for the central learning version of this, there is one party that can see both agents and everything, and they are just instructing them what to do in order to kind of like a coach, and this is the team, and the coach is just trying to tell the team how to achieve the goal, and
I see. Makes
each
sense.
individual is sort of only useful in their participation in the team. They're not, they either succeed or fail together in this case. So we're gonna look at actually like this forging example and see. Now, the authors of the book do have a code base. I can say I haven't actually looked at it in detail with how they do the forging task, but I was just trying to um, sort of sketch out how this multi-agent type structure would work, and then see how easy it is to make this, this sort of classic toy example in that framework. So, but once I finish with this, we'll be able to actually see what the action space and everything looks like for the whole problem. So here I'm just creating this foraging sort of module, which will contain everything relevant for this problem. So I'm just creating this foraging move type. So the possible moves are the four directions, the collect operation, and then no op, which is the agent doing nothing. The positions in this case are it's just an integer, it's just two integers, which is XY position where you are in the grid. And then the action list is just, this is just redundant. It's just all of these. Now, for the actual state of the environment, this has a little more information than is actually needed at a minimum. So what's really needed to define a state in this problem is the positions of the agents, the positions of the items, and then the levels for each of those things. Now I've added, so this is required because this state doesn't actually tell you the bounds of this, but for convenience or for looking up useful things later with forming like step functions, I'm just going to store a set of available positions, and this keeps track of the positions an agent can move by excluding the positions occupied by items. Then each item can only be collected by one of the adjacent squares here. So also for convenience, once I create an environment like this, I'm just going to store in the state like the adjacent positions to the item, so that way I don't have to calculate it each time. It's also important, notice how in this environment, these objects are far enough away from each other that an agent cannot be adjacent to both simultaneously. And that's important because if you look at the action space, there's the collect action. This doesn't say which item the agent wants to collect. So it's very important for these types of environments that an agent can never collect two items at the same time. There can only be one like possible collection item. So that creates a restriction on how close these items can be. And then for the purpose of normalizing these reward values, which is mentioned later in the book, we do need to know the level sum, which is the original sum of item levels, not like once we collect one item, it'll go away, but we need to sort of store the original, like in this case, it would be 3 for this problem. So yeah, and then we can form, yeah, this function is just one that allows us to form a state providing less information. So it like automatically calculates this other stuff, like the available positions and things like that. So far, like this is the same kind of thing we would do for a single agent problem, right? Because this just defines everything about the environment state. Now, all of this stuff for collecting, this is just, it looks a little complicated because you have to go through and basically check if an item is collectible and then figure out the order to do it so you're not like repeating a bunch of work. But basically, I go through all of the items here and, oh, sorry. So first, like I go through all the agents, and then if an agent is trying to collect an item, I store this reference that an agent of a particular level is trying to collect this item. Then later I go through and then check which, if any, of the items actually can be collected. And then, yeah, the movement stuff is pretty straightforward. This is just updating the positions, which is just adding, you know, moving in X and Y the appropriate space. Yeah, to initialize the state, this just places the items in such a way that I mentioned where they're far enough away from each other. And then in terms of making the whole environment, we have the grid. Now, the step function here, this takes the state and the joint action, which in this case is going to be this tuple of n integers, where each integer just says which action index each agent took. And then it goes through, it updates all the positions. So in the case where an agent isn't trying to move, the position will just stay the same. Then it doesn't actually specify this in the book. It might be more clear in the code base, but I have set it up so that after all the agents move, if any of the agents are in an unavailable position, meaning it's a position that is not in the grid, or it's a position that is occupied by an item, or if any of the agents have ended up in the same square, so they're now sharing the space, then I just reset their positions back to the original one. So it's like a failed move and they're unable to move. So there's no like order to this. Like if one agent tries to move into the other space and the other one moves, if two agents are both trying to move into a square that they would both be in, basically they both fail. It's not like the first one, because in these types of problems, these joint actions are supposed to occur simultaneously. It's not like the agents go in order. So whatever joint action that occurs should be something that works if it all happens simultaneously. And then, yeah, there's this thing that keeps track of whether a collection happened. And then if an item was collected, then it removes that item from the state, and it has to remove its level as well and update the available positions. But of course, items can only be removed from this problem. They don't have to be added ever. So at least we don't have to worry about adding new items. So this is to make a general one of these environments. This particular environment here is a little different because it always starts in the same position. the general one here is to make a more general level-based foraging example, which comes up later in the book. But for this example, there's only 2 agents, so most of this is the same, but I've just hard-coded some of these values. Like this is an 11 by 11 grid. There's only 2 agents, 2 items, and then they each have this particular level when they're initialized here. And then the step function. But what I did here, so this whole thing ends up defining a multi-agent problem that is actually not tabular. Here, like I've written this step function that takes a state and joint action and produces a reward tuple and then a new state. What in a tabular problem, I should be able to actually enumerate all the states and create this lookup table, right, of all the state transitions. And that's what I'm doing here with this example. So I have the step function from before. However, what I do here is I'm actually creating the initial state, which is always the same. Then I initialize a list of states, which is empty. And what I go through here is I'm basically creating an exhaustive list of all of the states that this problem can have, which means when I have these 2 items here, I position the agents wherever they could be in the grid, right? So I position the first agent in any available position, the second one in any available position that is not already taken up by the first agent. And then I just create this new state where I keep the item levels. But then I actually have to repeat that for the case where each item is removed. So there's only this item left or only this item left. And also the case where there's no items, even though that is a terminal state. But those are all equally terminal states. So this ends up creating an exhaustive list of states. And then I can actually create a tabular problem where I have, so in addition to enumerating all the states, this is filling in the state and reward transition map. And notice here I have 3 indices for both maps, right? This is the index of the action of agent 1, the action of agent 2, and then the state index. And because this is a deterministic problem, right, whenever you have a state and joint action, there's only one outcome. So it's deterministic. So here I'm just storing the deterministic state index that it ends up, and I'm also storing the deterministic reward that each agent gets, which in this case there would be 2 of them. And we can look at what this looks like. So this is the generic example I made, which is not the tabular problem, but we can see that for the multi-agent problem, the agent actions, so here I've just created an arbitrary example where there's 3 agents and each agent has the same action list, right? Which is just these 6 actions. Now, I had previously written that thing that converted this into a single agent problem. And that's what's being done here. So in order to convert this, I need to pass this multi-agent problem I've created. And the sum function means that I'm just going to sum the rewards, right, for both across the two rewards for both agents. And now we could see side by side these 2 different problems. So now instead of an action space for each agent, there's now a single joint action space, which is 216 length, right? Because this is 6 to the 3. And we can see here that this includes all the different combinations of actions between the 3 agents. And then the transition function, well, this is just still this. This will now be a different step function, but you can't really see inside of it because it's a function. But you can see the action space, how it's been transformed. So you see how this is the same as what I showed before with the Cartesian indices, going from 3 sets of 6 to now a single list of 216 joint actions. So does this make sense how the difference in the action space between the multi-agent problem and the single agent, or just the MDP version of the problem? So the tabular environment, you can see a little more into it. So now, in addition to this stuff, we now have a list of states as well. We can see for this problem, this state list doesn't have to be this big. I could have taken all the terminal states and just collapsed them into a single state, but for completeness, I just kept them all as distinct states. And there's 57,602 of them, which sounds like it is a pretty big state space, especially considering how small this problem is. It should give you an idea that this type of approach might not work if we make this problem more complex. But each of these is a different state. This 2 by 2 just means here there's two agents and 2 items. There's always going to be 2 agents for these states. Some of these will only have 1 or fewer items. Like here is 2 agents but 0 items, right? Because this is a state where both items have been collected. And then, yeah, but now we can just use the state index. So if we mean state index 4, it just refers to this state. Then we have the agent actions, right? There's 2 sets of 6. And then this is the transition function. So for the state transition map, right, it's a 6 by 6 by 57,000 or so array. And right, the way we look this up is we have, right, each slice here is for a different state. And then this is a 6 by 6 grid, which tells you in this state with this, whatever, 1 by 1 or 2 by 2 joint action selection, then we end up in state like 27, for example. But right, it's just integers here, which tell you which state you end up in. These are all terminal states, so you can see that they all end up in the same state after the transition. Now, for the reward transition map, it's the same size array, but now there's a reward for each agent, right? There's a tuple of 2 values, 1 for each agent in the reward transition map. So fine, this is the multi-agent tabular problem. So if we reduce it, like what I'm doing here, to just a tabular MDP, again with the sum function, now this just happens automatically. We can now do this for any multi-agent problem, but the state space is the same. The action space is now this size 36 joint action space. And now the maps are all matrices, and they just tell you for which joint action you pick, which state you end up in. And for the reward, it's for the joint action and whatever state you were in, what is the reward now sum between the agents. So now this is a proper MDP. Everything has been reduced to a scalar reward. Yeah, but so now for this particular example, like we can see exactly what this looks like when we have the multi-agent problem and then the single agent reduction to it. So but once we set all this up, now the advantage is we could apply this reduction to any multi-agent problem in the future. It looks like a lot of setup, but it'll end up paying off in the future. Here I'm just showing it for this particular like grid world example. So now that we have this MDP version, we can apply any technique we care about. And actually, because this is a deterministic and a tabular problem, we can apply an exact solution technique like value iteration. And that's what I'm doing here. They don't do this in the book, actually, possibly because they don't actually make this a true tabular problem. They may, or they might not actually generate all these transition maps. They may just keep it as like a sampling problem where the step function just tells you, like you can just sample from it, even though because this is a deterministic problem, right, we can actually enumerate all this. We don't need to just like solve it by sampling from the environment. But here we can actually solve it exactly with value iteration. And right here, like I literally just call it like I have a function already from this tabular MDP stuff. And all I do is pass in this MDP reduced version of the problem. And this is the discount factor for the problem. And then it does some sweeps over the state space. It solves it. Now we can see what the solution looks like. Actually, I should make this a little wider. So now that we have the solution, it does mention it in the book, but we can just verify that the tabular solution did in fact, do what it's supposed to. So here, right, this is all kind of upside down and flipped over just because of how I'm plotting this. Right, I'm just like, this is 1, 1, and this is 11, 11. I think in the book they have it where this corner is 1, 1. So it looks like I've just had this plot. This is the episode over time. So like once this has been solved, right, this ends up producing like a policy function, an optimal policy. I can then use this policy function to just run an episode in the environment, which will just produce the list of states after selecting the joint action. Now, this is what happens in terms of rewards. So there's a reward of 1/3 here, a reward sum, because I'm summing the reward between the two agents. And then this is a reward of 2/3 because it's 1/3 for each agent. So this is what happens over the course of the episode. I have this like slider bar so we can actually see what happens during each. Well, actually, wait, I have to uncheck this. So the episodes start in this state, and then as I advance this, what happens is the agents move. This agent first goes here, then it collects that item, and then it goes to the second item where the other agent meets it simultaneously, and then they both collect it, and they get this reward of 2/3. If we go back to the first step, the value function here tells us the discounted expected reward for this, which is 0.902. And right, the total reward sum is 1 for this problem, but we're using a discount rate of 0.99. So this tells us sort of that this is just relaying the fact that there's some number of steps required to solve this. This happens to be like 13 steps total to collect this, but part of the reward happens on this earlier step, on this like step 8, because this is all one step pushed forward in the future. And then this reward doesn't happen until step 13. And then we can also like just see how this works. So this problem is simple enough where we can actually just infer what the optimal policy is here, because we know exactly how long it's going to take each agent to reach each thing. But notice that the agent on the right, because it can't collect this item until this agent meets it, it actually can get there early. So there's actually quite a large space of equally good policies where it wastes some amount of time. Like it could just go straight to item 2 and then do a no-op for a few steps, or in this case, it actually, what does it do? Oh yeah, it just no-ops for the first 2 steps. But if I actually, where is the episode? But yeah, if I were to like regenerate this episode multiple times, the behavior of this agent would move. And also this one has a few options of how to reach this, like, right, it can zigzag however it wants because they're all the same number of steps to reach this. So we can see how this central learning approach does in fact solve this problem. But what they mention in the book is using, so we know like we can use an exact solution method. We can also use a sampling method. So here is an example of using SARSA, or Q-learning is like a variant of expected SARSA. Q-learning, we can actually use, here I just, this is training for 1 million steps total. And it just samples from the environment just like a normal single agent RL algorithm would operate. But here I'm just solving it with SARSA, expected SARSA, Q-learning, and double Q-learning as an example. And we can see here, so now this is just showing, like, you know, they all do an okay job doing this. This is actually showing the average number of steps per episode. So that's like how long it takes for the two agents to collect both items. We know from the exact solution that this should be 13 steps at best. And we can see with this, so it's 13 steps, and also the exact value of the initial state is 0.902. So that's like the discounted value across the sum of both agents from start to finish. Here we can see that these algorithms, it looks like the best performing one out of what I tested here is this double Q learning. Generally, the double learning algorithms do work better than single learning because they eliminate this maximization bias that happens with techniques like Q learning. But we can see that the performance it's achieving is not actually that optimal. I mean, it's like 21 steps. We know the best is 13 steps. If we go back to the book, actually, do they have this? So here's the learning curve from the book. And here they show the central Q learning is this curve. So this curve would correspond to all the techniques that I showed. The point they're making here is that the central learning actually performs worse than the independent learning because it has to deal with a larger action space. But here, from the exact solution, we saw that the evaluation return is just like the expected discounted value of the initial state. And we can see that the ideal value is like 0.9. So even this method, after it appears to have converged, we can see this isn't quite 0.9, right? 0.9 would be higher up here. So neither of these methods are actually getting the true, optimal performance. But so the point is, what we can use any RL technique, right? As long as we do this central learning reduction. The other idea from the book is to, actually, let me make this wider again, is to do independent learning. And the idea behind independent learning is that each agent learns its own policy and has its own value estimate based on its own actions. So from the perspective of each individual agent, it is performing a single agent RL algorithm, taking all the other agents and their behavior as part of the environment. And then if we look at this, this is the value update from Q learning, but here it's being done right for each agent individually. And then this has to be synced up as well. Like here it's showing it for just one agent, but see other agents choose their action. So this can only proceed forward, like this algorithm, once all the other agents have selected their action. So we can think of this as one big loop where we go through this and we do this update for all the agents individually, and then we just take the next step. And we can do this in parallel still with all the individual agents. So now each agent is trying to maximize its own value function, its own individual reward. And we don't have to apply this scalar reward function if we do independent Q learning. So we can certainly do this and try it out. But the question is, what will actually happen if we apply this algorithm? Now, for this problem, where we have, each agents do collect individual rewards for this problem. And we haven't, if in the multi-agent problem, right, we haven't created like a shared objective function. We've just given the ability of each agent to collect. And what happens when we do independent Q learning for this is that it does end up learning the same solution as for the for the centralized learning. So the agents do learn to coordinate together. It's a particular quirk of how this exact problem is set up, because obviously, like, from the perspective of this agent, which is further away from this item, it will actually never get the reward from this item because the other agent is going to it first. So, it's in its interest to cooperate on this item. But if you thought about this as like, these algorithms don't address the problem this way, but if this was a repeated scenario where these agents did this repeatedly, and they could observe their behavior over multiple rounds of episodes, this agent may, want to sometimes collect this reward, even though overall the reward sum would be lower. Like if they were instructed to both coordinate and get the highest reward, it never makes sense for this agent to collect this reward, right? Because it would take longer than if this one does it. And then you're wasting time. But, so I believe like this ends up working where it converges to the solution where you maximize the sum of the reward because of the structure of this problem. And there's this table in the book, this is a study of independent learning in the case of the games that are like this. Oh, sorry, this now is going to reformat. So these type of games where we have these two agent, two action games. And right, these games have different types of equilibrium solutions. This type of game will always have at least one Nash equilibrium, but the Nash equilibrium is not necessarily the solution that maximizes the reward sum. It could be that could be a different solution. And sometimes these games have deterministic Nash equilibria. This game is an example where there are two deterministic Nash equilibria where the joint action is AA, or like they both select the first action. And then there's another one where they both select this action. It's also shown here. And this welfare criteria, this is showing the sum of the reward for the different joint actions. So we can see this Nash equilibria, right, has the highest reward sum. This one has the lowest reward sum, or not quite. I don't know if it's the lowest out of anything possible, but it's the lowest of any equilibrium solution. Now, the question is like, which of these would a multi-agent system converge to? Like we would like it to converge to this one. Or will independent learning even converge to an equilibrium solution, right? It could end up converging. I mean, there's also this probabilistic equilibrium solution here. These techniques won't actually converge to a probabilistic solution because the policies don't have the ability to represent arbitrary probabilistic policies. They can only represent policies with maximizing actions, or where some actions are equally maximizing. But this table in the book shows for just that small subset of games, does it converge to an equilibrium solution? And by it, when they ask here, does IQL converge? So does it converge to begin with, right? Because it's also possible that the agent's behavior would oscillate during the learning process and never converge to anything. So we can see the conditions under which it converges, and then in this case, it wouldn't converge. So this is a case where there is no deterministic Nash equilibrium. And in this case, there is no Nash equilibrium, and there is a joint action which produces a better outcome than the one Nash equilibrium that does exist. And in this case, it just doesn't converge to begin with. The agent's behavior would just fluctuate. There's three cases here where it does converge. And like, this is a straightforward case where we have one deterministic Nash equilibrium, and there's a dominant action, which means there's an action which is always the best action for a player, independent of any other knowledge about what the other player does. And there is no other joint action which has a higher value. This is, I believe, the same problem class as actually, what do they say? Oh, 3A they don't mention. 3B is the prisoner's dilemma problem. And the prisoner's dilemma problem, the equilibrium solution is not actually the best like total reward that could be achieved. So this is a case where this might converge under some conditions or might not. But this is a major problem with independent learning, is that we can always set up and run this algorithm. But like if we do central learning, like this is guaranteed to converge to the optimal solution, but that optimal solution is defined by the scalar reward function. Whereas in independent learning, we've created a situation where what this converges to actually depends on the structure of the problem. And we don't know that ahead of time. And this table is only relevant for these really particular, narrow games, right? When we do the level-based foraging example, this is already a totally different scenario, right? We have 2 agents, but we have way more than 2 actions, and also there's more states. Like this isn't just a game with a single state. Yeah. So I have an example here of it's pretty easy to implement an independent algorithm. This is an example of just doing independent Q learning. So this basic loop steps through the environment, and here this actually isn't even running in parallel at all, even though like this could all be parallelized here. This is the part where it goes through all the agents and it does the value update using that agent's own value estimation function. Now, once the agents update their value, then they update the associated policy, which in the case of Q learning is just gonna, be the argmax or epsilon greedy with respect to the value function. And then, it'll sample a joint action now here, and then this is the part where it uses the joint action to create the rewards for all the agents and the next state in the environment. But this is like closely matching the independent Q learning in the book. And here's an example of running it. So if we add this curve in here, I'm not running these algorithms with the exact same parameters as was used in the book, but we can see that they're all basically managing. I'm now evaluating this independent Q learning using the same criteria as these, where I'm taking the reward sum and then I'm transforming that into the average number of steps it takes to collect it. So in all these cases, we're evaluating all this performance in terms of the collective success of the agents together, which is going to be like, how long does it take for them to collect all the items in the environment? So actually, even though the independent Q learning is simpler in the sense that each one of these value estimates, so here, this is the result of doing the independent Q learning. And you see that each agent has its own value estimate it's learned, which is for all the state action pairs from its perspective. From its perspective, it has 6 actions, and then there's the 57,000 states. So whereas for central learning, this is a 36 by 57,000 matrix. Let's see if we can. Yeah, so here is doing the Sarsa algorithm with the central learning, and we can see here that now the policy function and the value estimate is this, instead of the 6 by this, it's now 36, so it's quite a bit larger. So the advantage of independent learning is you don't have that exponential increase in the joint action space that you have to deal with. But, the disadvantages, as I mentioned, are you don't actually know, there's only certain problems where the algorithm will converge to anything. So yeah, we have those challenges. Okay, so I already mentioned some of the challenges, but the remaining, what's left of the chapter goes over you know, what are the main issues we're going to have to deal with when we come up with ideas for algorithms in the remainder of the book. And in multi-agent learning, definitely we are going to need to do some degree of independent learning, because the joint action space is just going to get too big for problems where we have a lot of agents. But then we have this non-stationarity problem where the agent's behavior is all changing simultaneously. We also have the problem of, if we do the independent learning, what equilibrium do we reach? First of all, can we even converge to an equilibrium? And if we do we converge to the equilibrium we actually care about? Because if there's more than one, we may converge to one that doesn't actually maximize the thing we care about. Yeah, this is just explaining. Yeah, well, when we think about MDPs, right, the transition function should have the Markov property, so it should only depend on the current state. Whereas if we're doing this with multiple agents, all of the agents' behavior end up contributing, right? With the independent learning, the other agents are impacting that. So it's not going to be a stationary process. It's going to change in time, and yeah, the single agent can't distinguish what is the same about the environment versus what's being affected by the behavior of the other agents. This is showing, oh yeah, I mean, this is actually showing a successful example where in the rock, paper, scissors example, both agents with independent learning are able to converge to the correct policy, which is selecting actions randomly. But if you have a different type of problem, right, these two agents may fluctuate back and forth in the policy space and never actually converge to the same thing. Yeah, actually, this stag hunt game is the same one I showed in that other notebook where there were the multiple equilibria. And yeah, they don't go into here, but this is an equilibrium solution. So is this. This one gives a better reward for both agents. However, adjacent to this equilibrium, like, this is true assuming both agents have correctly calculated this equilibrium. But there's also a risk if an agent chooses this, if the other agent deviates from this behavior, right, it could end up being bad for the first agent. Whereas if an agent ends up in this equilibrium, they're actually guaranteed that if the other agent changes, their reward only goes up. So this equilibrium is less risky in a sense. It's actually less risky during the learning process. It's not less risky overall, because once you're in this equilibrium, neither agent will deviate. But during the learning process, there's some amount of random choices that can occur. So that's a case where independent learning could very easily converge to this equilibrium instead of this one, even though this equilibrium is more beneficial for both agents, right? But when we do independent learning, there's nothing about that algorithm which optimizes for a welfare optimal equilibrium. It'll just, if the game is the right type of game, converge to one of them. But the claim here is that it's actually more likely it will converge to this one because of that risk issue during training. And then, yeah, I mean, these are all issues that'll come up later of how do we actually assign credit. I think, yeah, like, so if we're learning where we look at the joint action space and we have a value estimate for the joint action space, then we can see hypothetically, like, what do we expect to happen if we pick this action, but the other agents pick other actions? When we do independent learning, like is shown back here, right? Each agent is only storing this state value estimate based on the state and its own action selection. So this value will account for all the behavior of all the other agents as a sample of their behavior, but we can't actually disentangle the impact of individual agents. Now, there are other algorithms where we still do independent learning, but each agent attempts to have a model of the whole joint action space, right? Like that's another option, but we need a way of updating those values. But in order to disentangle like the attribution problem of understanding, how much of a step outcome actually depended on other agents' behavior versus our own behavior, we need a way of modeling, not just these independent action spaces, but more of the joint action space. And there's just some examples here. Yeah, where like if you don't have the joint action, estimates at your disposal, then you just simply don't know if something was successful because the other agents did something that made you successful, or if your action primarily is the reason why it led to a good outcome. But all these things at the end of the chapter are really just are just references for the algorithms we're going to deal with later in the book. And the next chapter deals with what they're calling foundational algorithms. So the two example algorithms in this chapter are, the single agent reductions. They don't really involve anything from game theory, right? Like this, we're just using these Q estimates and we end up converging to whatever or not if it doesn't work. This, we just eliminate the game properties by generating a scalar reward. In the next chapter, we're going to look at algorithms that actually use some of the stuff we developed in chapter 4 about game theory. And that's where like these algorithms are, rather than just being single agent reductions, are going to be particular to the multi-agent problem and the states themselves being like stochastic games. You can see here, this is like value iteration for stochastic games. So what I showed here was this solution to the level-based foraging problem, right? Where I actually applied value iteration here. So this is like normal value iteration for MDPs. And I was only able to do this because I reduced the problem to an MDP, right? So for the next chapter, we're going to look at the equivalent to this algorithm for stochastic games, where now it's actually not doing a MDP reduction of the game, but actually using the properties of the game. And really, this piece here is actually going to compute an equilibrium solution. Gee. I think it mentions it here, but I believe we'll try to cover this next time. I don't know if we'll actually get through this entire chapter next time, because I think this has a lot more material than chapter 5. And we can see like Nash Q-learning. So now we're actually going to look at properties of the games where we explicitly try to compute an equilibrium solution, rather than just, hoping that we end up in an equilibrium. So are there any questions about chapter 5, what we covered, and the single agent reduction stuff? I think the most important part of this chapter is just understanding what it means to take a stochastic game and turn it into an MDP, and how that technique where you convert the problem to a tabular MDP, this will not work for stochastic games that are zero sum, right? Because in that case, the scalar reward that we use, if we use this sum as a scalar reward, then every single step will always have a reward of 0, which means that there is nothing to learn about the game. And then we'd have to rely on one of the techniques that we'll get to in the next chapter, where we can actually compute equilibrium solutions. So, but if you do have a problem, which, you can there is some scalar reward function that makes sense to you, then you can transform it, like with the stuff I showed here, into an MDP, and then you can apply like, the entire library of techniques from reinforcement learning to solve it. Like I showed, here, like this value iteration, obviously. The nice thing about this is it runs faster and it immediately just finds the exact solution, whereas all the sampling techniques in the book, like none of them actually converge to this optimal value, like 0.9. Okay, so yeah, next time we'll cover some or all of chapter 6, and hopefully, yeah, I'll see some of you there. Yeah, are there any other questions? Yes?
Yeah, I just had one quick question. So, like, how would you go about finding the types of problems that you want to solve using Q learning? So, like, for example, just like what problems would you say are ideal for Q learning?
Q learning. You mean like from single agent reinforcement learning?
Sure, it could be single agent, multi-agent.
Well, in multi-agent there is, so the independent Q learning is this, single agent reduction we looked at. So if you have an environment with full information, meaning like you can write down all the probabilities of all the transitions, then you don't have to do Q learning. You can just use something like value iteration, which is an exact solution method. Q learning you would use if you have a tabular problem, so you can enumerate all the states and all the actions, but the actual dynamics of the environment you can only take samples from. Like for all the transitions where a state action pair then transitions to a new state, that we can't actually write down exactly what happens. We just have a function that we can sample from. And in that case, because Q learning is a technique that learns by sampling from the environment. But the advantage of Q learning is that you calculate estimates for all the state action pairs, so then you don't need a model of the environment to solve it. You can just learn all those state action pairs by sampling. But in multi-agent learning, there's other Q learning style algorithms, like in chapter 6, I guess we'll get to, yeah, so like value iteration. So this, like they start out with an exact solution method. So like this you can use when you have this full transition function here. And then for Q learning, like this is an example of like minimax Q learning, Nash. Oh, I guess they don't have pseudocode for these. But these would be other cases where then we're sort of applying the same game theory calculation, but now we're just observing rewards, right? Like here, like observe joint action rewards. So now we're just sampling from the environment and we're saving the information from the samples in these Q estimates. So you would always need to use some kind of Q learning technique if you have a problem where you're just restricted to like collecting samples from the environment. So I'm not sure if that answered your question, but Q learning is like a pretty broad range of techniques, but they all involve saving estimates for the action values. Okay, well, if there's no further questions, then we'll stop there, and I hope to see people next time.